In my last video, I discussed symmetric encryption, which uses the same key to encrypt and decrypt, but we ran into an issue. How do we deliver the key to our client? That's where asymmetric encryption comes into play. Now, asymmetric encryption can be a little hard to understand, so I'm going to start with a simple analogy. Let's think about a mailbox. Anyone can just walk by and drop in a letter. No special key is required, and the contents of all the letters in the box are secure. So anyone can send a letter, but they can't read other people's messages. The only person who can gain access needs a private key to unlock the box. Now, to be fair, this is kind of a weak analogy, so let's see how this actually works in practice. Unlike symmetric encryption, asymmetric encryption uses two keys. Let's use a web server as an example. When a user makes a request from the browser, the server will send the public key. This key is used to encrypt the data. So in this example, the word hello is converted to a big number. On the server side, the private key is used to decrypt the message, so it can be processed by the server. So why do we need two keys? Let's say a hacker is intercepting our messages. They would also have access to the public key, but since that key can only encrypt traffic, they wouldn't be able to view the message. So you might be wondering, how does this even work? In my previous video, I talked about the Caesar cipher, and everything was pretty intuitive. You have a key that encrypts and decrypts by essentially reversing the cipher or the algorithm. So the idea that one key can only encrypt but can't decrypt is a little hard to understand. So let me explain. Asymmetric encryption works by using something called a trapdoor function. A trapdoor function is a mathematical operation that's easy to compute in one direction but difficult to reverse without some specific information. So I know that sounds a little abstract, so I'll use another analogy. Imagine you have an empty glass. Now let's fill it with ice cubes. It's pretty easy to figure out what the outcome is going to be. You're going to have water in the glass. However, if you start with a glass that's filled with water, it's harder to reverse the operation. I mean, where did the water come from? Did you fill the glass from the sink? Did you put ice cubes in the glass? How many ice cubes? And what were their shapes? It's not impossible to figure out the answer, but it's also not very easy without specific information. Now let's create some keys to see how this works. So what we'll need to get started are two prime numbers. Usually these numbers are huge, but we'll start small with 5 and 11. In the next step, we'll multiply the two prime numbers together to give us something called the modulus. The modulus will be part of both the public and the private keys. And since it's contained in the public key, you don't have to worry about keeping it secret. A quick side note, if a hacker can successfully guess just one of the prime numbers, they'll be able to recreate the private key using the contents of the public key. And at that point, they'll be able to decrypt your messages. The reason they only need one number is because the modulus is readily available in the public key. Since the modulus is the product of both the prime numbers, all the hacker would have to do is divide the modulus by the known prime number to get the other prime number. Okay, getting back on track. Once we've calculated the modulus, we want to compute a relatively prime number called a totient. Now it's up to us to select another prime number, but this number has some requirements. It has to be less than the totient, but also a coprime. I picked the number 7 because it's less than 40, and if you try to divide 40 by 7, you end up with a remainder. So 7 is the perfect candidate. Okay, we're almost there. Combining our new prime number with the modulus gives us our public key. So that was a little bit complicated, but hopefully not too bad. Next, let's create the private key. First, we have to figure out what the private key exponent will be. To do that, we'll use something called the extended Euclidean algorithm. Don't worry about the details right now, just know that it's a recursive function that solves for the variable d. To make things a little easier, you can use a programming language like Python to easily compute this. Solving this equation gives us 23. If we combine 23 with our modulus, we get our private key. Just a reminder, the private key decrypts our data, so make sure to keep it safe. Now that the keys are created, let's see how we would use them to encrypt and decrypt some data. Let's start with encryption first. In case you couldn't tell, asymmetric encryption uses a lot of math to perform its operations. So for our first step, let's convert our data into numbers. In this case, let's convert the letter C into the number 3. Next, we'll use our public key to encrypt the number 3 into 42. Now let's zoom in a bit to see how this works. Here we have our public key and the number that we want to encrypt. To encrypt, we use this formula. So let's take this one step at a time. X is the number that we want to encrypt, which is 3. We'll then take X and raise it by the exponent from our public key. Finally, I'll take the modulus from our public key and plug it into the modulus section of the equation. Now, you might be wondering, what is this thing? Why is there a percent sign in the equation? This is called a modulo operator. I know this is a little confusing. You have two words that both start with mod, so let me explain. First, let's talk about simple division. If you divide 8 by 4, you get 2. It's clean and there's no remainder. However, if you divide 9 by 4, you get a value of 2 with a remainder of 1. The percent sign, or the modulo operator, divides a number but only returns the remainder. And the number you divide by is called the modulus. So to recap, modulo is the operation, and modulus is what you divide by to get the remainder. Okay, now that we know what all the terms mean, let's start plugging in some values. We'll set x to 3, and again, this is the number that we want to encrypt. Next, we'll grab our exponent from the public key, so that's 3 to the power of 7. We'll then set our modulus to 55. If we do the math, we'll get 42. So we encrypted 3 into 42 using our public key. Next, let's use our private key to decrypt the message. Okay, so the number 3 was encrypted with our public key, and the result is 42, which is going to our server. But now we're running into that trapdoor function problem. We have to reverse the operation, which isn't easy to do, unless we have a specific piece of information. And that specific piece of information is our private key. Let's take a closer look again to see how this works. The decryption operation is nearly identical to the encryption equation, except this time instead of x, we have y. We'll start by plugging in these values again. So we'll take the encrypted value of 42 for y, and we'll raise that to the exponent from our private key, which is 23. Both keys have the same modulus, and I'll drop that into the equation just like before. If we do the math, we'll get 3, which is great because we've just decrypted 42 back into 3 using our private key. Now I want to show you something interesting. What you see here is everything we just talked about, but is Python code. And just like before, I'm taking the number 3 and encrypting it to 42, and using a private key to decrypt it back into 3. So everything is working as expected. But what if I increase the size of the number that we want to encrypt? Instead of 3, let's try 100. Again, I'll run the encryption and everything looks okay, but when I try to decrypt, something has gone wrong. It doesn't seem to work. The point I'm trying to make is the size of the key matters. You can't encrypt data that's larger than the size of the key. And that's okay because our goal is to first set up asymmetric encryption and then use it to encrypt the symmetric key. Once the server has a symmetric key, all the traffic is then encrypted with symmetric encryption. Symmetric encryption is also more efficient compared to asymmetric encryption. It can handle larger data sets while using fewer resources like CPU. So the goal is to switch from asymmetric encryption over to symmetric encryption as soon as possible. To wrap this up, I want to show you what an actual public key looks like. This is an example of a certificate that would be sent to your browser, but in this format called PEM, you can't really make out what it's doing. So we'll use a tool called OpenSSL to inspect the contents. And scrolling down a bit, you can see that the public key is embedded in the certificate. This block is called the modulus. The formatting may look a little strange, and that's because it's a byte array, but you can think of it as just a really big number. Below the modulus is the exponent part of the key. This number is kind of significant, 65537. Public keys will often choose this number as the exponent because it's fast to compute, and it's a prime number that's guaranteed to be relatively prime to the totient. So it's in kind of a sweet spot. Okay, I think that's a good place to stop for today. In the next video, I'll dive into public key infrastructure, or PKI. Using PKI, I'll walk through the process of creating TLS certificates. Thanks for stopping by, and I'll see you in the next video.